I welcome you guys to the first lecture on Maths 110, and the first topic we'll be treating in today's class is sets. So, according to your manual, um, a set is any collection of objects such that, given an object, it is possible to determine whether it belongs to the collection. So, in simple sense, we can say that a set is the collection of well-defined objects. So, for the Department of Accounting, we can say that all of the students, they are set. The reason is because every student in the department has unique matriculation number attached to their name. So this is a set. So another example we'll check here is capital letters. Capital letters denote set. That's one of the properties one of the properties of a set is that sets are always represented in capital letters. So you cannot see a set being represented in a smaller letter. So that is that. The second thing is that sets are denoted by curly brackets. So the notation of set is always in a curly bracket. You can't represent set in any other bracket apart from curly bracket. Now we have what we call a finite set. A finite set is a set that has all of the members or all of the elements to be countable. So when we say 1 to 20, 1 to 20 is a finite set. While, of course, otherwise of a finite set, we have the infinite set. So the infinite set is a set with an infinite number of elements. If A is an element of A, we write A as AEA. You can see that symbol that you have there represents membership. It is called membership, or it is called element. So we say that Ahmed is a member of accounting department. Wale is a member of mathematics department. Shola is a member of accounting department. So that member, instead of you saying member, you use that symbol there to represent membership. And of course, otherwise, if you say Daniel is not a member, it simply means that you are underlying that membership symbol. So I believe we get that. Now moving on to set notations. Set notations. When we say set notations, what we simply means is that different ways by which we can represent set. So the first way we can represent set is the roster or enumeration notation. So the roster or enumeration notation is the listing. It means you are listing all of the elements. So if we say list all the elements, all the members of your department, you'll be able to list them, write their name. So that's why it is called in form of a roster. So if your department or your lecturer asks your HOC to give a roster of all the members of your class, so it's going to represent them in a roster notation. So you can see we have 1 to 5 and 2, 4 and 10. Now moving on to semantic definition. So the semantic definition is what I already gave earlier as an example of your your lecturer demanding for all of the members of your class. So A is the set of the first 4 positive integers. D is the set of department in the Faculty of Social Science. Are you getting it now? So set builder notation. Set builder notation is another way that you can represent sets. So you can see now that, let me read the statement of F for you. This is how you read it. F is equals to S such that X is an integer and 0, X is less than equals to 10 and greater than equals to 0. So you can see, you can as well change this set builder notation to a lister form. So what they are saying here is that you are listing all of the members of F. So if you want to list this one that they wrote here as in a lister form or in a roster form, you are going to start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So that is F. That's how you are going to list it. Are you getting me? Another example of set builder notation is the even numbers from 2 to 10. So even numbers from 2 to 10, you necessarily do not need to write all of the numbers, start listing. Of course, everybody knows that if you are to list all of the even numbers from 2 to 10, it's going to be 2, 4, 6, 8 and 10. But instead of you writing 2, 4, 6, 8 and 10, we have now discovered a simpler method or a distinct approach that can be used in representing even numbers from 2 to 10. So instead of us writing this, we decide to write it as S such that that line that you see there, that black line that is slant, that is straight, is called such that. So S such that S is equals to 2n and n is equals to 1, 2, 3, 4 and 5. Now you notice that if you put the value of n inside s equals to 2n, you will still arrive at all of the numbers, all of the even numbers from 2 to 10. Can we check? If you put n to be 1, you have 2 times 1. 2 times 1 is 2. If you put n to be 2, you have 2 times 2. 2 times 2 is 4. If you put n to be 3, you have 2 times 3, 6. If you put n to be 4, you have 2 times 4, 8. If you put n to be 5, you have 2 times 5, which is what? 10. So this is set builder notation. Are you getting me? So I'm going to give you one to practice. So you should, in case you've done it, you can put it in the comment section. So this is the one you practice. You are going to practice for odd numbers. So you use s equals to 2n plus 1 for odd numbers. Are you getting me? So if you have that, you can drop that in the comment section. Meanwhile, before we continue, before we move down to types of set, I have already compiled all of the exercises for this chapter 1. So if you are ready to get all of the exercise, you can just slide into my DM and you ask for it. Thank you. So moving on to types of set, we have different types of sets, a whole lot of them, but these are the limited ones for your level. So the first one we have is the singleton set. As the word implies, singleton means a single element, just one set. The second one is empty set. It is also called null set. Some people also call it the void set. Are you getting me? So now the next one, subset. When we say subset means that it is also called containment. Are you getting me? So A is a subset of B, means that every element of A is also in what? In B. The other one is called proper subset. As you can see, please take note of the symbol. Proper subset. For a proper subset, A is a subset of B, and A is not equals to B. Are you getting me? A is not equals to B. So this means that it is not necessary that all of the elements in A cannot be equals to all of the elements in what? In B. So that's what we mean by proper subset. Now we have power set. We have what we call power set. Now before power set, there is something called cardinality. Cardinality of a set means that if I give you 1, 2, 3, 4, 5, this is 5 elements. So the cardinality of those elements is 5. If I give you A 1, 2, 3, 4, 5, 6, what's the cardinality of those numbers? The cardinality of those numbers is equals to 6. If I give you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the cardinality of those numbers is also what? 10. Are you getting me? Now, moving down to power set. Power set, the formula for power set is equals to 2 raised to power of the cardinality. So 2 raised to power of the cardinality, that n that you have there is also called the cardinality. So power set is equals to 2. That 2 that you see there is a constant value. Is the formula for power set. So you don't need to ask where is the 2 coming from. 2 is the formula for power set. 2 raised to power n. So if you are finding it, for example, if I ask you to find the power set of 1, 2, the power set of 1, 2, the first thing you are going to do first is you find the cardinality. How many numbers do we have there? We have 2 numbers. So because you have 2 numbers, the power set is going to be 2 raised to power 2. 2 raised to power 2 is going to be what? 4. So this means that all of the power sets that you will be deriving from this example is going to be 4 members. So as you can see, the power set of 1, 2 is you are going to start from the empty set. You now pick from 1. You now pick from 2. You now pick from 1, 2. So if you count all of the elements that we have there, now you see that there are what? 4 different elements, from null set to 1 to 2 to 1 and 2, which is the set itself. So if it is 3 elements, 1, 2, 3, the power set is going to be 2 raised to power 3. If it is 4 elements, the power set will be 2 raised to power 4. So I believe we get that. Down to basic set operations. When we say basic set operations, we have the union, we have the intersection, we have the complement, we have the difference, we have symmetric difference, and we have what we call the Cartesian product. So union means that you are bringing everything together. Are you getting me? Union means you are bringing everything together. So union means if you have your brother and your sister and you are coming, or a man and a woman. When we say the union between a man and a woman, it simply means that you are joining them together. So a typical example is, a mathematical expression for this is that if you have A to be 1, 2, 3, 4, 5, and you have B to be 5, 6, 7, 8, 9, 10, the union of the two of them is going to be 1 to 10. Are you getting me? Now that's that for union. So for intersection is simply the common value. Are you getting me? Now, for example, all of the students in your department, you have something in common. One of the things you have in common is the course that you are doing. Are you getting me? Is the course that you are doing. That's what you have in common. Or you can consider a class of students or a school. So what all of the students have in common is what is their uniform. Are you getting me? So that's intersection. Now for the complement of a set. Now when you are dealing with complement, okay, before that, the mathematical expression of union of a set is S is such that S is in A. I'm reading that mathematical expression in front of it. So for those of you that want to learn how to read that, so you read it as S such that S is in A or S is in B. Another way of reading it is S such that S is a member of A or X is a member of B. Are you getting it? The same thing for intersection too. S is a member of A and S is a member of B. So you can see union is or, intersection is and. I get me. Now, for complement of a set is highly dependent on the universal set. Universal set is the mother set, is the king set. I get me. So anywhere you see complement, you are simply referring to the mother set. So the mother set means that you are going to take away the given set from the mother set. Don't worry, we'll come to complement of a set. So moving down to difference of a set. Difference of a set is still the same thing as normal difference. If I ask you to take difference between two things, of course, that subtraction, you are going to just subtract. Are you getting me? So difference of a set means S is in A and S is not in B. That's difference of a set. So we are going to do more examples so you get to understand most of these things. Now for symmetric difference is highly dependent on difference of a set. So that's why you see that after you take the difference of the set, then A minus B union B minus A, or A difference B union B difference A. An alternative way of finding symmetric difference is that A union B minus A intersection B, you will still arrive at the same answer. So for symmetric difference has, when you see that symbol, that triangular symbol, that's symmetric difference. But for Cartesian product is often represented with a multiplication symbol. So you see A cross B. So A cross B means that you are multiplying A and B together. You are bringing in A and B together. Are you getting me? So A comma B such that A is in A and B is also in what? B. Are you getting me? So that A, that small letter A, is a member. Why the capital letter A is the set itself. That small letter B is a member. Why the capital letter B is the set itself. So take note of that. So whenever you are dealing with set and you see small letter, that small letter is the member, is a member of the set. Why the big letter is the father of this, is the mother of the set, is the set itself. Are you getting me? Now, moving on to basic properties of set. Now, we have 18 of them, and I must confess that it is very important for you to note most of them, because there are probabilities that most of your questions might not necessarily be coming from calculation. So if you see, you probably might be asked to recognize which of these is a property of set. So the first one we have is A union B, which is equals to B union A. So it simply means that union of a set is commutative. Are you getting me? The same thing goes for intersection. Intersection of sets, they are also commutative. Right? Now, the third one is called the associative property. The first two, they are called commutative property. The third and fourth, they are called associative property of set. So associative property of set has to do with three different sets. So you can see A union B union C. We pick A union B first, and similarly is equals to A union B union C. So that's what we mean by the associative property. So you can see we are done with the commutative property of set. Then we now move to the associative property of both union and intersection. Now, moving on to 5 and 6. 5 and 6, they are called subsets. Are you getting me? Not proper subset. Proper subset does not usually have that down part. It's subsets that has the down part. So you can see that. So A is a subset of B if and only if. So there is a condition to it. So you can see theoretical questions like, which of the following is correct if A is a subset of B? So the criteria, the condition necessary for that statement to be true is that A union B must also be the same thing as B before you can say that A is a subset of B. The same thing goes for number 6. Number 6 is A is a subset of B if and only if A intersection B is equals to what? A. So moving on to 7 and 8. 7 and 8 is they are vice versa. So you can see A intersection B union C. We open it. It is called, number 7 and 8 is called the distributive property of set. It is called the distributive. Number 1 and 2 is called commutative. 3 and 4 is called associative. 7 and 8 is called distributive. I don't know the one for 5 and 6. 5 and 6 is just subset. I get me, but 7 and 8 they are called the distributive. So we distributed intersection. Intersection was distributed in number 7, while in number 8 union was distributed. Are you getting me? So the remaining ones that we have, 9 to 18, they are very important. They are just very important properties. So number 9 is A is a subset of B if and only if A intersection B complement is empty. And the number 10 is A union A is equals to A. If you take union of yourself, is still yourself. If you take intersection of yourself, you still get yourself. Number 12, if you take union of an empty set, you get that set back. If you take intersection of an empty set, you are going to get empty set. Please take note of 12 and 13. Most people usually confuse 12 and 13 a lot. Reason because A union, if you take union of an empty set, you are going to get back that set. But if you take intersection of a set and an empty set, if you take, intersection means common term, and there's nothing common between empty and a real set. So the set is empty. I get me. Now number 14 is A union universal set. That U that you have there is universal set. And A union universal set is also universal set. Number 15, A intersection universal set is A. Number 16, A complement. So complement cancels out. They cancel each other and you go back to the set. Number 17 and 18, A union B complement equals AC intersection BC. A intersection BC equals to ACU BC. So practice these properties. Of course, they are very essential. So moving on to example number 1. Example number 1 says that let the universal set be U 1, 2, 3, 4 down to 18 and S equals to 2, 6, 18 and Y is 1, 3, 6. We are asked to list the element of X intersection Y. So by listing the element, okay, we've already stopped everything here. So you can see the element common to X and Y is 6. So S intersection Y is 6. S union Y is 1 to 18. S union Y is 1, 2 down to 18, which is also the same thing as our universal set. So from the properties that we listed earlier, so you can see that number 3 is true. So if you take the union of X and Y, the union of X and Y with respect to the complement is still going to be empty set. I get me. When we took the union, we got the universal set. And when you take universal set means that complement means you are subtracting universal set from universal set. And when you subtract universal set from universal set, you are going to get what? Empty set. Down to the next question. Solve the example 2. So this example is on Venn diagram. So you have to pay attention and you must be very logical. One thing that you should always do when it comes to Venn diagram question is that first thing you do is you locate the intersection, the midpoint. What is common? That's one trick I use in answering any Venn diagram question. You always locate the intersection first. So if you read the question now, the Venn diagram shows the choice of food of a number of visitors to a canteen. Use the information to answer the following question. If there were 35 visitors, find the values of X. So we have people that ate rice, people that ate plantain, people that ate yam. Now locate the intersection. The intersection is 2. So the intersection is 2. It simply means that it is only 2 people that ate